Welcome back. In my previous video, I have defined what is the improper integral. I have defined Cauchy introduced extended of concept of Riemann integration. When the range of integration is infinite, also when the function is unbounded in the range, or these two both conditions hold, then this is called improper integral. In my previous video, I have seen different type of example. Also, I had seen when improper integral converges or diverges. Today, I will say improper integral elaborately. Also, I will say some example which had come in different type of competitive exam. The idea of improper integral and concept of improper integral actually very important for higher study. So, at first I will highly recommend you, if you don't see my previous video, at first see my previous video. Then today's video would be so easy. Improper integral. In my previous video, I have seen integration a to b fx dx is improper when either the range a equal to infinity or b equal to infinity, or both a equal to infinity and b equal to infinity. And for this condition, fx is bounded. And this type of improper integral is called first kind improper integral. And when fx is unbounded at one or more points of in this interval a less than equal to x less than equal to b, that means in the range, then this type of integral, improper integral, is called second kind of improper integral. Today I will discuss this type of integral. In my previous video I have defined first kind of improper integral, or other maybe both one and second type both. In my previous video I have seen first kind of improper integral when converges. If fx be a non-negative integrable function when x greater than equal to a, and integration a to m fx dx is bounded above for m greater than a, then integration a to infinity fx dx will be convergence. Otherwise, if the limiting value of this integration is infinity, then this integration is divergence. In my previous video I have seen for plus infinity. Similarly, for integration minus infinity to a fx dx equal to, we can write limit m tends to minus infinity. Here integration m to a fx dx, and here x obviously less than a. If this integration exists, then we can tell this improper integral converges. Also for this case, integration minus infinity to infinity fx dx, if we can write this as limit m tends to infinity integration minus infinity to m fx dx plus limit m goes to minus infinity integration m to infinity fx dx. If both integral exist on the right hand side, then obviously this integral, integration minus infinity to infinity fx, exists, and we can tell this improper integral is convergence if both integral exist. And if any one of the right hand side will not exist, then integration minus infinity to infinity fx dx will not exist, and obviously this integral is divergence. I hope my all viewers have understood this type of concept easily. When one improper integral converges, when one improper integral be diverges. Okay? Well. For example, consider the integration minus infinity to infinity x e to the power minus x square. We can write this as minus infinity to 0 x e to the power minus x square plus 0 to infinity x e to the power minus x square. Then at first evaluate integration minus infinity to 0 x e to the power minus x square. This value would be limit a tends to minus infinity integration a to 0 x e to the power minus x square, and this value is actually minus half. And I2 equal to integration 0 to infinity x e to the power minus x square. This value is limit b tends to infinity integration 0 to b x e to the power minus x square, and after evaluating the limit integration, this value would be half. Therefore, I have got I1 equal to minus half and I2 equal to plus half. Therefore, this value of integration I, which is equal to I1 plus I2, this value would be minus half plus half, which is 0. And since this value is finite, so we can tell this integral is convergent. Okay? I hope my all viewers have understood this concept easily. Okay? Well. Now evaluate the value of integration. Integration 0 to infinity sin x dx. We can write this as limit m tends to infinity integration 0 to m sin x dx. And integration sin x means obviously cos x minus cos x. Therefore, limit m goes to infinity minus cos x. Here the integration from 0 to m. So, evaluate the value from 0 to m. This value is limit m goes to infinity 1 minus cos m. Okay? And since cos infinity does not exist, so this limit does not exist. Therefore, this improper integral is divergent. Now evaluation the improper integral of second kind. Integration a to b fx dx, where obviously the function fx is unbounded. Consider fx be unbounded in the interval closed ab, but bounded and integrable in every interval closed ax, where x less than b, and the graph is such type. In the interval a to x, the function is bounded, and in every point of this interval, the function is integrable. But when the function reaches at the point b, then the function is unbounded. Then, if limit t goes to b minus 0, integration a to t fx dx exists, then we can say integration a to b fx dx converges, otherwise it is diverges. Okay? Thus we have integration a to b fx dx. Since here at the point b has an infinite discontinuity, therefore we can write as limit epsilon tends to 0 integration a to b minus epsilon fx dx. That means this is the point b where this has a infinite discontinuity. This point is b minus epsilon. When epsilon tends to 0, then b minus epsilon goes to b. And if this limit exists, then we can say this improper integral a to b fx dx, where fx is unbounded at the point b, then we can tell this improper integral is convergent. Okay? Well. Similarly, if A is only point of discontinuity, similar to before, here A is only point of discontinuity of fx in the closed interval AB, then integration a to b fx dx equal to limit x goes to a plus epsilon integration x to b ft dt, and which is actually equal to limit epsilon goes to 0 plus integration a to a plus epsilon to b fx dx. And if fx is unbounded in an arbitrary small neighborhood of a point C such that a less than c less than b, that means fx has a discontinuity at the point C lies between a and b, then integration a to b fx dx equal to limit epsilon tends to 0 a to integration a to c minus epsilon fx dx plus limit epsilon dash tends to 0 integration c plus epsilon dash to b fx dx. If both limits exist, then integration a to b fx dx exists. Okay? That means there exists various type of discontinuity. Here discontinuity at the point A, at the end point A, here discontinuity at the interior point C. Now consider I equal to integration 0 to 1 dx over square root of 1 minus x square. Notice here 1 is only point of discontinuity. So the integration would be such type. Limit epsilon tends to 0 plus integration 0 to 1 minus epsilon dx over square root of 1 minus x square. And this is actually sin inverse x. Then limit epsilon tends to 0 plus, and this value would be from 0 to 1 minus epsilon. Now put the value. This value would be sin inverse 1 minus epsilon minus sin inverse 0 limit and the limit epsilon tends to 0, here limit epsilon tends to 0 plus, then this value would be sin inverse 1 minus 0, which is equal to pi by 2. And since the value of the integral is finite, that means this improper integral is convergent. Now evaluate integration minus 1 to 1 dx over x cube, if this limit exists or not. Notice at the end point minus 1 and 1, the function is bounded. Only the function is unbounded at the point 0. That means at the point 0, this is the point of infinite discontinuity. So break this integral such type minus 1 to 0 dx over x cube plus 0 to 1 dx over x cube, and consider this is I1 and this is I2, where I1 equal to minus 1 to 0 dx over x cube. Since here at the point 0 is the point of discontinuity, so right now this can be written as limit epsilon tends to 0 plus integration minus 1 to 0. Since here the discontinuity in the upper limit, so this can be written as 0 minus epsilon dx over x cube. After integrating and putting the value of limit, this value would be minus 1 over 2 epsilon whole square plus half, and limit epsilon tends to 0. If we put the limit, then this value would be unbounded. This limit tends to infinity. Similarly, I2 equal to integration 0 to 1 dx over x cube. Since here the discontinuity at the point here below point 0 So this integral would be limit epsilon tends to 0 plus 0 plus epsilon to 1 dx over xl cube. And similar to before, after integrating and putting the limit, this value would be limit epsilon tends to 0 plus minus half plus 1 over 2 epsilon square. Similarly, this tends to infinity after putting the limit. Therefore, I1 plus I2, this value is infinity. So, this improper integral is divergent. Okay? Oh well. Now I will see comparison test for improper integral. Comparison test for improper integral applicable for type 1 integral. Integration a to b fx dx. Here, since this is the type 1 integral, that means fx is bounded and consider a equal to minus infinity, b equal to or b equal to infinity. Or a and b both minus infinity and infinity. Then comparison test of improper integral is, suppose f and g are integrable over the interval a, close interval ac, where for all c greater than equal to a and a greater than equal to 0, less than equal to z. This is true for all x belongs to a. Then now I will see this convergency. Integration 0 to infinity cos x over 1 plus x squared dx. We all of us know, for all x belongs to R, cos x always less than equal to 1. Therefore, if fx equal to cos x over 1 plus x squared, we can write this is less than equal to always 1 over 1 plus x squared. Now, consider this 1 over 1 plus x squared as a gx. Therefore, the relation fx less than equal to gx, this is hold for all x belongs to R. Therefore, now we have to find the convergence test of function gx. Integration 0 to infinity gx dx. Here, since here infinity, so this value would be limit m tends to infinity. Integration 0 to m dx over 1 plus x squared, and after integrating and putting the value of limit, then this value actually tan inverse x, and this is 0 to capital M, limit m tends to infinity. After putting this limit, this value would be pi over 2. Therefore, since this value is finite, that means this improper integral converges. And since gx converges, therefore by comparison test, we can draw this integral where fx is this always converges by comparison test. I hope all viewers have understood comparison test in better way. Now I will see another similar type of example. Integration 0 to infinity sin square x over x square dx is convergent. At first, break it two parts, 0 to 1 and 1 to infinity. I have broken it two parts because integration 0 to 1, this function is proper integral. We have to only find this part because this is only improper integral. And here I will use the comparison test. We all of us know, since sin x less than equal to 1, therefore sin square x over x square less than equal to 1 over x square. And in my previous video I have seen integration 1 to infinity 1 over x to the power n dx is convergent for n greater than 1. Okay, and notice here 1 to infinity 1 over x square where n equal to 2. Therefore, this is convergent always. I hope my all viewers have understood this part easily. Okay, similar type of example. Here the improper integral is integration 1 to infinity x minus 2 over x cube plus 1 dx. Notice x minus 2x over x plus x cube plus 1. We can write this is less than x over x cube plus 1, and x over x cube plus 1, this is also less than 1 over x square. And notice, we all of us know integration 1 to infinity 1 over x square be convergent. Therefore, by comparison test, our given improper integral this is convergent. My all viewers have understood how comparison test will be used to verify of an improper integral be convergent or divergent. Okay? Oh well. Today I will stop here. In my next video, I will discuss limit comparison test of improper integral. But at first I will hardly recommend you, please see today's video with pay attention. Then you will understand in my next video in better way. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.